go to the downstairs?
Yes.
Thank you.
All right. Bro. All right, Sachi's not here. Zach? Yeah. Oh, I was doing attendance. Friends are here, Jill's here. All right, so just Sachi. All right, hello, my lovely student. Oh, Mr. Late One snuck in. There he is. All right, so we are going to finish up with Unit 6 today with something called Improper Integral. What's the vibe on snow tomorrow? What are we thinking? Cancel?
Okay, here's the thing. I have a hot take on this.
Hot take. I'm ready.
The snow is supposed to be reported at less than an inch, right? But it's gonna start.
Is it really? I thought it was like 1 to 2. Yeah, Jay just said.
Yeah, Jay.
There's probably gonna be happening. So all we need is the rain is gonna go from like 2 a.m. to 6 and it's gonna snowing at 6.
Okay. See, but that's bad timing. That's bad timing. It's not gonna be cold enough.
And it'll be icy roads. And I'm just praying that those are carries.
All right, so we're gonna look at the schedule and everything in a second. Because right now, why do I even talk? Hi, I like the double wave. That made me feel very welcome. Hello. My hair is bothering me today, so thank you. No. I'm sorry. I feel very consistent with the braids because I just need it out of my face. All right, so we're going to be doing 6.5 today. I'm going to warn you, I'm kind of finagling the schedule because you guys are kind of doubling up on lessons, and B-Day hasn't even done 6.4 yet, and we're doing 6.5 today. So if we're out of school tomorrow, Friday may be a work day on our problem sets. So just putting it out there that the schedule is probably going to get adjusted. I wouldn't mind us pushing the Unit 6 test back until the first week of third quarter too, because remember that's not going on this quarter. And I already know next week is going to be stressful for you guys. I would like to, if the test does end up falling next week, I would like to reiterate something that I do mention to some people, but I often forget to mention to the whole class. If you ever have a day where you've got like 3 tests going on, 4 tests going on, and my test is one of them, talk to me before that day and we can reschedule my test. I've done that for some people this year. I've done it in the past. Just putting it out there, if the test does happen to be next week, but you've got a really stressful day, if you're talking to me beforehand, that is an option that we can do. So, but I'm going to try to make sure, yeah, what's up?
Are you thinking the top of the thing get pushed back from Friday to another day or not?
I don't know yet.
Is it due for this Friday?
Yeah. Currently, yes. So. All right, let's go through the current dates. Here are our current dates. So we have done trig integrals. We're doing improper today. Technically, problem set is supposed to be due on Friday. And test would be the 25th, which is next Tuesday. We're going to see what happens. This is the current schedule, though. So if you have not opened your problem set, maybe do that. So we're going to be doing improper integrals today so that you'll be fully prepared. But before we get started, how long is this tape measure?
12.
I have this one.
All right.
I really hope it's
Would anyone like? Thank you for raising your hand, Mason.
Yeah, James said 16.
16 what? Is that feet?
Oh, feet.
I don't know. Do meters? Really?
No, I know. Laura and I are together on really.
20?
20.
Yeah, Michael.
45.
Wait, I'm on with
30?
I'm also at 30.
Yeah.
Oh, no, I haven't been, okay. Can I do 50? 50? That is not 50. I'm telling you now that it's not.
Very long.
I don't know. Me and Julian are for 30. Where can I print
This thing is this small.
Thank you.
Come on, we're gonna fly down. 5.
Oh no, that's not what I got. Did you get this one? I messed it up.
I'm gonna go with small, so let's cross out.
I don't know.
16. All right, ready for reveal?
Yes. He has it more So, what is it? It's 12 feet. Oh, no.
All right. What we will be doing, Austin? Yeah. All right. What we are going to be doing today is something called improper integrals. I'll pass out the notes in a second, but the actual integral process isn't going to be difficult. I will say today is a lot about notation. So if we ever fight about you not having good notation, today might be a good day to pay attention because this is pretty much all about notation today. We're going to do two things. We'll take a break in between. Improper integrals are one of two things. Either one or both of the bounds are infinity. Those are kind of a little more obvious. Or the function that we're working with in our integrand has a vertical asymptote at or between the bounds.
I was going to say, did you start your video?
I did, thank you. And I am recording. You're the best.
I find your videos very helpful, so I
Yeah,
want to
is anyone watching the videos even?
Yeah, I watched it.
Okay, cool.
I
I'm trying to decide if it's something I want to do in the future, so.
I think you should.
I need to find, does anyone have a better, anyone else need 6.4?
Yeah.
I'm
just gonna walk around with 6.4 in my hand, so if you were not here last time, let me know.
We were here.
I knew that this had to be taught because I measured about this big.
It doesn't matter.
Right here.
So if I can see kind of like, so I'll try, maybe I'll do it. The thing is, you haven't tried that all. I don't know, it seems faster than what's for you, but just, it's like.
I usually like work my way up.
Yeah.
And then I go. Like, oh, pause it. It's going to go fast.
One and a half, I actually right now.
Yeah.
Maybe I'll leave it at, I don't know, I tried not to pause it, and then I paused it, and you're very good. Maybe I do that. Like, I'm not actually sure how much that is. Not, it's like,
I just like it. Like, I like it.
Yeah.
Yeah, I realized you did
All right. Are we ready? Cool. So I'm going to tell you, we're probably not going to do the last page of this notes because it's a little aggressive. So we're probably looking at 6 problems today. We're going to start with the ones that are easier to see that you have to do this process, and then we're going to get to the ones where it's a little bit less obvious. Like I said about kind of all of these methods, the hard part about this is realizing when you have to do it, and then kind of just getting the notation right. So the reason we're starting with the ones that have infinity in the bounds is it's a little more obvious you have to do this process. If we see infinity in our bounds, infinity is not a number that we can kind of plug into a function. So we have to use some notation to say, hey, I would like to plug in this number, but I'm not actually allowed to plug in this number. So I'm just going to see what happens when I get really, really close to it. Is any of that language reminding you of something that we usually talk about in calculus? Like, hey, I want to plug this thing in. I can't, so I'm going to get really, really close to it and try to figure it out.
Limits.
Yeah, we often use limits to deal with asymptotes, so that is a good also connection there. We're going to be dealing with asymptotes soon. But really, this is all about a lot of notation with limits. If you're annoyed by this notation, I really don't care. You have to use this notation. If you don't use the notation, I can't give you the points that you want. That being said, if you get to the AP test and it's a multiple choice question, a lot of my students in the past have said, can I just plug in infinity like a bound if I'm on a multiple choice? Sure, I don't care. On a free response, though, this is what you got to do. So what we're going to do is we are going to first limit out our bounds. Now, I use certain letters just because of the way textbooks do. So I'm always going to limit out A for the bottom bound and B for the top bound. You can use whatever letters you want as long as they're not in your equation or your integral currently. So I'm going to say the limit as B, because I'm replacing the top bound, approaches infinity, 1 to B of, and I'm going to rewrite the integrand to be 1 over x dx. So literally the only thing that's changing is this right here. The reason we're doing this, infinity is not a number, so I can't treat it as one. So I'm just limiting it out. Again, that B can be whatever you want as long as it is not X or a letter that already has a value like E. All right. Now this gets really easy. We just want to do this integral. So the limit's going to stay. He just chilling. And we're going to integrate the inside. Tell your neighbor, what is the integral of 1 over x? Oh, wow. I was eavesdropping. Natural log absolute value of x from 1 to b. You love today? Well, that makes one of us. I'm working on it. Algebra 1 was kind of boring this morning. Graphing inequalities. It's my least favorite unit. Hello. What do you think I'm going to do next? What? We already integrated. How about plug in the bounds? Which bound goes in first? The top one. I ask you because some of you are still plugging in the bottom bound first. Please stop doing that. Super awkward. All right. Now, I'm going to keep the absolute value bars around the B. I know it's a little aggressive because I know I'm shoving B towards positive infinity, but since B is a letter, it's a I should stop saying letter. Since B is a variable, I'm just going to let it be real specific. All right. 1, though, I know is a positive number, so I'm going to leave it there. Now, this is kind of the hard part about improper integrals is I do have to know a little bit about limits as I go. So I've selected problems today that kind of get to some of the values that I'm going to need you to know. One of them is this, as b approaches infinity, natural log of b, where does it go? Impressive. All right, so let's do a little aside over here. I hate that bathroom. All right, so I'm going to do a little bit of an aside over here, if you'd like to. This is one thing that I'm going to need you to know. As we take natural log, as we take the innards to infinity, where does this go? Does anyone think they know what the answer to this is? It is infinity. Let's talk about why. Does anyone know what the graph of natural log of x looks like? All right, let's start with the graph that's a little bit easier. Does anyone know what the graph of e to the x looks like? It starts little and it gets real big, right? It starts little, it gets real big. Exponential growth. The cool part, that's actually, I really hate that. I'm going to round to that guy. Yeah, they're opposites, they're inverses. So they reflect across the line y equals x. So this is what the graph of natural log looks like. All right, this line y equals x. If you can rephrase that question, I would love to answer it. I'm not sure what you're asking right now.
Natural log graph.
Uh-huh.
Is it supposed to be the other way? It's constantly approaching the x?
No. It looks like that, I promise. This is y equals 1. This is x equals 1. So that corresponds to like natural log of 1 is 0. We're going to do that in a second. But as you can kind of see, if I extend this line going this way, natural log of x is a very slow growing function, but it does grow towards infinity. So this is one fun fact you need to know. As I approach infinity on the inside of that natural log effectively of infinity is infinity. So as I plug this in, this first term that I have circled in green is trending towards infinity. All right, if it happens again, someone's going to go check on them and make sure. Are you okay? What? Okay. Does anyone know what natural log of 1 is? I said it a second ago. 0. So, interesting answer here. I get infinity as an answer. What the heck does that mean? What does an integral mean again? Area. So that means the area of the function 1 over x from 1 out to infinity is too big to give a number to. Let me show you that graphically. So we got 1 over x was my function, if you will, that I'm trying to accumulate area on. And if I'm looking, so let's do this. Y is less than using the inequalities that I did this morning with algebra 1. All right, so this is the area we're talking about. We're talking about this skinny guy as I take this all the way out to infinity. So we're accumulating a smaller and smaller sliver of area. But what I'm claiming is that if you tried to buy some blue paint to paint this entire thing from 1 out to infinity, there isn't enough paint. There's never enough to paint this whole thing because it has infinite area. How exciting. So there's actually a word to describe this if we get a form of infinity, and that word, which we will use a lot in the future of BC calculus, is that this integral diverges. How do you know if something diverges? You either get infinity, negative infinity, or for some reason you can't integrate it. You're really just talking infinity or negative infinity. Yeah, like Divergent, the movie.
This is really good.
No. Yeah. Not my favorite casting choices. It really is. It's really bad. All right. Are you guys ready for another example? Is this an improper integral? Why? All right, we've got negative infinity in a bound. So I'm going to use A for this one just because it's the bottom bound. That's my trend. That's my thing that I like to do. You could use as long as it's not X because that's in the integral or something like E that already has a value. You could use J for Jessica. I would also not use a letter that looks like something that'll make you confused. So like
an O.
yeah, like an O, that'd be tap. Some people don't like I's. If your handwriting's bad, just use like yeah, like L. No, you could do this L. Yeah, you use Greek letters.
Hieroglyphics for that. Oh no, that was before.
Yeah, I've had smiley faces, hearts.
Really? Because you won't get it mixed up with anything else.
Yeah. All right. Hello. Hi. We need to integrate this. Anyone see a problem as we integrate this? Why did I highlight the 2x? All right. Chain rule, if it was a derivative, what's the opposite of that for integrals? U sub. Now, I would argue this is probably a U sub that most of us can do in our head at this point, but if it's not, let's talk it out to the side. If I set u equal to 2x, what would my du be? 2 dx. Do I have that 2 in my integral? No. So I'm just going to chuck a 1/2 out front. Now, the advantage to kind of doing this either off to the side or just not really fully substituting, I don't want to have to change my bounds here because I've already got bounds that are letters. I could do that and just make my bounds 2a and 0. That would be fine. But just to be really clean with my integral, I know this is just going to shove a 1/2 in front of whatever I would originally integrate it as. So I'm just going to do that. As Nike says, just do it. Or du it. Wow, so many jokes. All right. So my integral, anyone brave enough to tell me what my integral is going to be? All right, e to the 2x. What else is going to be there? The 1/2. So think of it like the opposite of chain rule. You would have multiplied by 2 for the chain rule. You're multiplying by 1/2 because we're going in the opposite direction.
Oh, so instead of multiplying by the 2.
It's almost like it's supposed to make sense. What should I do now? Which bound goes in first?
The top bound.
All right, I'm going to simplify as I kind of plug in. So as I plug in the top bound, do you guys agree that's going to be e to the 0 times the 1/2? So e to the 0, can we all agree that's 1? So this is just 1/2 for the first term. Minus, now I'm going to plug in the bottom bound. And just like before, I'm going to do some kind of scratch work off to the side to deal with this guy as I'm plugging him in. I don't want to plug in negative infinity to that a, because the whole point of this limit is that we don't actually plug in negative infinity. So anytime I'm trying to evaluate these limits here, I'm going to do it off to the side. This time, instead of thinking about a graph, I'm going to think about like chicken scratch work of if I did actually plug in negative infinity. But notice I'm not doing this within my regular problem. So you agree negative infinity times 2 still pretty big, still pretty negative. All right. What do negative exponents do? Okay. So I got like 1 over 2 times e to the infinity. All right. So I've got 1 divided by something so super huge, we could call it infinity. Where is that trending towards? Okay. So notice I'm doing that work off to the side. Here, I'm going to say this is 1/2 from this 1/2 right here, minus 0 from the e part. That's the part that's getting set equal to this guy. So I get the answer 1/2. Now, since I got a number, not infinity, this integral does something else. Anyone know the other word? Converges. Now, most of the time, what I'll ask you for is to state if the integral diverges. But these words are going to become very much part of our vocabulary, not in the next unit, but the unit afterwards, which is all about convergence and divergence tests for series. So we're just going to be adding a bunch of numbers instead of integrating. But I'm just so excited to teach you guys that unit because it's my favorite one. So converges just means you get a number. So infinity, yeah. Yeah, so don't make those words more complicated than they need to be. Most of the time, the only reason you're going to need to know either one of those words is just if you get infinity, you're going to say that it diverges. All right, let's do one last question, and this one's going to be the hardest one. Why do you think it's going to be the hardest one? We have 2 infinities. Now, have we ever done 2 limits sandwiched next to each other and just like done the whole problem with 2 limits out front? No, that's super weird. So what we're going to have to do is we're going to have to split this integral into 2 different integrals so we can limit each bound separately. Is this annoying? Absolutely. So this will not happen very often, but I just want to show you what happens if you do. Yeah. You might be able to do that in multivariable. Since we're single variable calculus, we're going to have to split this guy. Yeah. So we're going to split this to go to negative infinity to something. I would have to look that up, Austin. It's been a real long time since I did any multivariable myself. All right, so cool discussion. We're going to pick a number to put in that yellow spot. As long as the number is the same in both yellow spots, we can choose literally whatever number that we want, because we just need to split our integral somewhere between negative infinity and infinity. It literally does not matter what number we choose. We will still get the same answer either way, but we have to choose a number. Does anyone have a recommendation for what number to choose?
0.
I like Michael's choice. When I can choose 0, I'm going to choose 0. But if you wanted to choose 7, if you wanted to choose pi, if you wanted to choose e, it doesn't matter. But thinking of things I like to plug into functions, 0 is my favorite thing to plug in, so I'm going to go with 0. But just as a note, that number can be literally anything you want. It just has to be between the 2 original bounds, and those bounds make it pretty easy to make that choice. All right, limits. I need to limit out the negative infinity. in the first integral. The nice part is we are integrating the same function twice. So once we figure out one of the integrals, it's going to be a little bit easier. I'm also choosing this integral very much on purpose because there are specific values that I need you to know from it. One reason I do like choosing A and B as my limit letters is in the case of this situation, I do have two separate letters for my two separate integrals, so I can't really get confused on either of them. If I had chosen like B and B, then I have B going to negative infinity, B going to positive infinity, which is a little weird in my brain, but whatever. All right, tell your neighbor how to integrate 1 over 1 plus x squared. Don't say the words natural log. Natural log. All right, anyone have any ideas? All right, we could try U sub. What would you set as U? All right, let's try it out. So that makes du 2x dx. Is that going to work? No, I got too many x's in my du. I did tell you what might happen if there are too many x's in your du. You didn't like the answer, but... What? Is someone whispering arc something? Yeah, it's one of the arc ones. Does anyone remember which arc one it is? All right, how do I tell the difference? Sine as the square root. This one is arctangent. Now, I can almost guarantee you one of the questions on your test will integrate into arctangent because arctangent does very cool things as you go to infinity. So if you want to tell yourself, hey, I got a test coming up in like the next 2 weeks, I need to know how to integrate this into arctangent, wouldn't be a bad idea. Do you guys mind if I immediately go and plug in my bounds? So I would like to write in the next sentence arctangent of 0 minus arctangent of A. Is everyone cool with that? Okay. If you're not cool, right. So we're not using U sub because it didn't work. We don't have the x in the numerator that we need. If you find your du has more x's than your integrand does, arctrig is a definite good place to go. Okay, so I'm just going straight to plugging in my bounds just to save a step of writing because this question has a lot of writing in it. If you need that second step of integrating then plugging in your bounds, definitely you do you. Every time I say you do you, it just makes me think of you du from whatever. What's the yeah. So that's integrating into arctangent. So just like 1 over x goes to natural log, 1 over 1 plus x squared is the derivative of arctangent x. Mm-hmm. If we had like a 9 here, that would be like 1/3 over 3. Remember the a and the u that we did before? We can practice with some more of those before the test. Did I answer your question, Connie? Okay. Anyone know what I'm going to write in the parentheses here? Bold takers? Good. All right, so I told you that this page was a lot about values that I needed you to know. So arctangent, there are 4 values that we really need to be aware of. So we're going to investigate those now. I think I might graph this for you so we can investigate on the graph. So all of this green stuff that I'm writing down is like values we need to know. All right, so I'm going to graph it on Desmos in a second. But we need to know, I'm going to use that. No, I won't use that notation. Here are the things we need to know. We need to know where arctangent goes as I go to negative infinity. We need to know where arctangent goes as I go to positive infinity. Cool thing, they're different. We need to know arctangent of 0, and we need to know arctangent of 1. So we're going to find all these out. The two at the bottom we've actually done before, because this is equivalent to saying tangent of what angle equals 0 and tangent of what angle equals 1. Does anyone know where tangent equals 0 on the unit circle? 0. So arctangent of 0 is 0. Does anyone know where tangent is 1?
270.
All right. 1. Do we ever work in degrees? No. So your answer should have a pi in it. Where are sine and cosine exactly the same? So when I divide pi over 4. All right. That's because tangent of pi over 4 is 1. If this feels rusty, go look at your unit circle. Just to show you, let's see if it takes this notation. These two things are exactly the same, just so you know. That is one thing the AP test will tell you. All right, so the question becomes, does it look like this graph goes to a very, very specific place as I go out to infinity? Does it look like there's a specific y value as I go this way that it's going to? Does it look like it goes to a very specific place this way? Does anyone think they know where it goes? Okay, so it looks like it's somewhere between 1 and 2. Let me graph tangent for you. So we're actually taking one of these, and just like we did with the natural log of x and the e to the x, these are inverse functions. You can see the y equals x kind of going through here. So the places I'm looking for are the places where tangent had its asymptotes. Does anyone remember where tangent had its asymptotes from pre-cal? Pi over 2. So what is happening here? This guy is pi over 2 at the top. Where do you think we're going as we go this way? Wow, y equals negative pi over 2. So these are the 4 values that I now need you to know. So this guy is negative pi over 2. This guy's pi over 2. One thing that's helpful, if you're doing arctangent at all, you should be answering with an angle. So that's a little bit helpful. But here's my graph to support my reasoning. This guy is my pi over 2. This guy is my negative pi over 2. And we will definitely use this guy when we get to the other unit about converging and diverging series, just because this is one of the very rare functions that does pretty cool things as we go towards infinity that we also know how to integrate into. So let's use all of that knowledge to figure out the rest of this integral. Let's see if you just remember. I'm going to put it away. All right. So arctangent of 0, that's just a number. The limit's going to go to itself. What was arctangent of 0? All right. Arctangent of A is going towards negative infinity. So where does arctangent go as we go towards negative infinity? Negative pi over 2. Arctangent of B as B goes towards infinity. What is arctangent as we go towards infinity? Pi over 2. And then arctangent of 0 again, 0. So notice these two values, this first and this last, are both that arctangent of 0. So it didn't matter what bound because we ended up adding and subtracting it. So our answer here, that's positive pi over 2 plus positive pi over 2. So pi. Follow-up question. Does this integral converge or diverge? Converge. Why? Because we got a number. Let's think graphically what this means, though. 0 is less than equal to y is less than equal to. All right, so here's the area that we're talking about here. These little spindly guys go all the way out forever and ever. These like pointy ends. So this graph, as I'm going out to negative infinity, so imagine that end going forever, that end going forever. If I'm thinking like every 1 square unit, I guess, is a gallon of paint, I can get this painted with 3.14 gallons of paint, even though it goes forever. So if I'm thinking paint, there is a finite amount of paint that will paint this infinite area. Kind of cool.
That hurts my brain to think about.
Just wait. There's actually, we can do it in the next unit. There's a shape called Gabriel's horn. Let me show it to you real quick. It's pretty cool. It is a shape that has finite volume but infinite surface area. So if you, mathematicians who have too much time on their hands. So this is called Gabriel's horn. It starts here and goes forever in that direction. If you poured paint inside of it, you could pour a finite amount of paint inside of it. But if you tried to use that paint to paint the surface area, you would never have enough paint. No, it's because it has infinite surface area but finite volume.
Is it like
Finite volume, infinite surface area.
so how
Mathematicians come up with these things so they have too much time on their hands, so that way I never
Yeah.
have enough.
Do you actually remember how much like paint you put in?
No, but I can figure it out while you guys are on your break. Depends on your scale.
It's like I'm just certain.
All right, so we're gonna take our break right now. The reason I'm breaking this into 2 pieces, and I'll kind of zoom out so you can see. So I think these ones are the easier ones for improper integrals because it's really not in like actual difficulty of the problem, but in realizing you have to do it. So these ones are easier because if you see infinity in your bound, you're like, oh, that's infinity. I got to do this whole thing. Whereas these next questions are going to require the same process, but it requires me to know that I need to do this process. So we're going to do this when we get back. The problems aren't any harder. Actually, I would argue that these 3 are a little bit easier because we're not going to deal with arctangent again. But just know that we're adding a step where we need to check every time we have an integral with bounds if this is the process we have to do. So, how about we take 4? If you need to go to the bathroom, now's the time.
My thought is does it get so thin that like doesn't fit through it? Like is that
No, it's thin enough, but it doesn't get covered.
Yeah,
We can look at it again next unit. So our next unit is going to be about rotation and surface. Well, we won't do surface area, but we can do. So you end up doing the volume is that graph is 1 over x as you go up. So it's like, let's say you start at 1 to b. So you do pi r squared for the area.
what's that number?
Versus the volume.
That B is going.
That's an infinity.
Oh, okay. It did look like that.
You do pi r squared for that guy, but the surface area. How do you do surface area again? You gotta do like I don't even remember how to do surface area. It's been so long. Oh, you gotta do your somehow this ends up being a 1 over x squared, so after you integrate the x is still enough.
denominator, and this one, the x ends up adding to the denominator in an actual log. So this thing ends up going to. So, I don't know how you do first here, because it's not part of the AP test anymore. Oh, my lord. So you guys use,
That was like, I don't know, did you find, no, he's left that phrase aside. The loft can be, the loft is all that remains in his house.
Oh, man, I can't believe what my friend did.
So our can looks like this, like it's like this, like the.
Would you do this? Come here. Would you do that? Yes. Let's see what God's surgery.
So you're basically for that, you're just trying to find like the area of it when you don't know how big it is.
Yeah, I mean, that's the kind of physical context of it. If you were gonna like actually look at it, we're really just gonna be working with like, hey, here's an integral, integrate this, find me a number.
University, I got it all.
I mean, if this modeled some sort of like rate of change and you wanted to find an amount of something, absolutely. Would you do it by hand? Probably not, but here we are. Exactly. I mean, that's most of what the C part, like the C part of calculus, the vast majority, like everyone is never going to actually have to do this. It's cool though.
It is very cool.
That's kind of the point. Proving you can learn stuff, right?
Are we in the C part of the contract?
This is not top maybe. Kind of though, because B is technically like integrals.
Can you have like from the end of the from being like step one to step two?
This would definitely keep top two.
Yeah, so is that out to
Yeah, so integrals get split over Calc 1, Calc 2, so this is definitely unlike the Calc 2.
So when did you realize like who does that?
Multivariable, who's gonna take that? Every engineer will.
Oh, engineer.
A lot of the time, pre-med will, well, pre-med definitely needs this.
I know you didn't reach out on it too. I wasn't sure. That's why.
Depends on the school. Every engineer will take that. All right, hello. We ready? All right, so the other type of improper integral, we are going to be integrating over or possibly kind of ending at a place where a function has a vertical asymptote. Now, how do we think with your like algebra 2 grade? You learned how to find vertical asymptotes in algebra 2. Does anyone remember how to find? That's where our function is undefined. Denominator equals 0. Essentially, that's the only thing we're going to be looking for. So notice that all of these examples, I know the last two are the same, but really you're looking for a place where your denominator equals 0. Now, the hard part about that is you're now going to have to be skeptical of any integral I give you that has bounds in it. Because I'm not going to say, hey, whoa, watch out. It could be an improper integral. You're going to have to check for that. The hardest part is when that happens between the bounds, but just be skeptical of anything I give you that's a fraction. Now, it's a little annoying because we did partial fractions. We did a bunch of integrals that are logs that have fractions. So you're just going to want to be very skeptical of anything you see with bounds. So let's look at what we're doing right here. Do you guys see a problem with one of those bounds? The bottom bound. That's an issue, right? I can't plug 0 into this function. So we could have the case where we can't plug 0 into the integral of this function either. So what we're trying to find, let me give you a graph just so we can put a physical context on this. Yeah. Usually. There are other instances. I can't think of any off the top of my head because the ones we're going to be looking at are always fractions. But I could like tangent would be a good example. Tangent has those asymptotes at pi over 2. Now, would I do that? No, because the integral for tangent is super weird and nasty. Anyone remember it? Integral of tangent? See, I knew it. Negative natural log of cosine. Right? All right, so we're doing this guy, and we're going zeros less than equal. Did I have to memorize all the rules?
Yeah.
Yep. All right, so theoretically, this is like the area that we're looking at. Now, does everyone notice that x equals 0 looks a little funky? All right, so we've got a vertical asymptote here. So just like our graph with the infinities was going like infinitely this way, we're now talking infinitely this way. So we're talking about, does this graph get close enough to this axis that I can kind of say, okay, all of this area is equal to a number, or is it too slow? And how I'm going to do that is just integrate using this limit notation. So I'm going to limit out the bottom down here. There is one little caveat that we will get to in a second. So not x. I'm going to go a since it's the bottom bound. A 1 over cube root of x dx. Now, there is one thing we have to do that we didn't have to do with infinity that usually doesn't make too much of a difference, but sometimes will, so we're going to do it every time. Theoretically, we are not actually just approaching 0. We are only approaching 0 from one side of kind of our x values. So does anyone remember one-sided limits? What did I put on my number? A little plus or a little minus, right? So looking at this, am I coming at 0 from the left-hand side of 0 or from the right-hand side of 0? The right-hand side. So I'm going to put a little plus right here. If you want to write down something to kind of prove that to yourself, one way to do it is to put your two bounds on a number line. We're looking at this little portion of area, so you're coming at 0 from the positive side. So that was a little shorthand that I kind of made up for myself to kind of figure that out. But you're thinking I'm coming from the top down towards 0, so I need that plus. Now, it most likely will not matter if that plus or minus is there in the end result of your integral, but sometimes it will. So we're going to always do it, partially because we want good notation. All right, now that we've limited this out, any thoughts on how we're going to integrate this? Probably the easiest integral we've done today. Okay, yeah, let's move it. Let's move the power. All right, I hear some powers floating around. Thoughts on how I could bring this up to the numerator and not make it a cube root? Excellent. All right, how do I integrate x to the negative 1/3?
In the inverse.
Okay, gotta have a new power first. What's my new power? No. All right, I'm gonna let you talk to your neighbors for about 10 seconds, and I'm gonna ask you again, and I better hear the same number. Mason? Okay. You leaving? Bye. All right. What's the new power? 2/3. Was that your answer? What did you have? Okay. Okay. Did you subtract one? It was close. Okay. You want some redemption? What goes here? Okay. 3 halves. No. All right, you may be thinking to yourself, wow, I'm really annoyed with this notation. Do I have to write that limit every time? Yes. You may be thinking, well, if I don't, what's going to happen? It's almost like you're reading my mind. All right, which bound goes in first? Top bound. All right, 1 to the 2/3. That's just 1. So this is 3/2 minus 3/2 a to the 2/3. Now, one kind of nice thing about when they're numbers, it's harder to realize you have to do this, but I think the limit at the end is a little bit easier than some of the infinite limits. So is 0 going to cause any problems as I plug in 0 to the 2/3 power? Is it going to be weird at all? Can I take 0 to the 2/3 easily? Yeah, you can. 0 to any power minus a negative power is fine. That's just 3/2 minus 0, which, as long as you're not doing negative powers. So I get 3/2. It converges. So we got a finite area. Thrilling. No, so usually the directions will stay integrate if the integral diverges, state that. So I would just peek at the directions. If it says state if the integral converges or diverges, then you'll want to state it. Yep, so I'm integrating between 0 and 1. So it almost makes a little more sense if you look at this guy. If I'm looking at this, do you agree that I only care about the values of x that are greater than 1? So I'm coming at 1 from the right-hand side. If I wanted to come at 1 from the, or excuse me, come at 0 from the left, you would want to see the area on the left-hand side. Yeah.
So when you do one bound and the other bound, continuous 3/2, where's the second group? That would be filled for x.
Yeah, I just plugged in the a for the x.
Oh, and it's 3/2.
Mm-hmm. Yep. So it's not 3/2. I'm just putting this a in for this x.
Oh.
That's still from the power.
Yeah.
No, you're good. No need to be sorry. All right, let's do another. Anyone have a prediction as to what the answer to this question is going to be? If you've been following the pattern, you probably know. All right, thoughts on this one? Is this an improper integral? I mean, it's on the improper integral notes, but sometimes I put examples that aren't. What makes this an improper integral then? The bound of 0. 0 is not allowed because 0 would make my original denominator 0, which is a no-go. So I'm going to limit it out. Let's go the limit as a approaches 0. Now, you guys had a great idea to rewrite this as a power last time instead of a fraction. What power could I rewrite it to this time? No. Good. All right. What's one thing that I'm missing? The plus or the minus on my 0. All right. I care about this between 0 and 2. Do I want a plus or a minus? Plus. I care about numbers that are greater than 0. So I'm going to use plus. Yeah.
Oh, how do you know when you need to add a plus?
If you're using a number. So infinity and negative infinity, there's only kind of one way to go at those. Here for the numbers, we're going to want a directionality. Thank you. I was about to do that. All right. What am I going to do next? Integrate. Oh, Bill. We got 30 minutes. Fine. Are you guys going to complain about how terrible your A days are? Like all of my B day students do? all of my B-Day students are like, this is the worst day ever. I hate all of my classes. I'm like, you're in my class right now. There's a different set of rules. I don't know what they are because I am not in charge. There's a committee this year, so we're like they're adults if they need backup for anything. We're gonna have a meeting soon. A lot of things are changing from the district level right now. So if you're using a number at all right, can I answer a question for the whole class because I've gotten it a couple times now and I want to make sure everyone's very in tune to why I have to do the plus or minus. So I'm going to do this plus or minus every time I use a number as I'm limiting. Think of infinity when we did it before. There's only one way to go towards positive infinity. You're coming from numbers that are below it. There's only one way to go towards negative infinity. You're coming from numbers that are higher than it. Numbers, there's two ways to go to those numbers. You're going to kind of see why this is important in this step. So anytime you're limiting out a number for your vertical asymptote, you're going to want a plus or minus there. All right, so now, yes. Someone tell me, how do I know if it's positive or negative again? Yeah. Okay. Yeah, so you can think of a picture, you only care about numbers that are bigger than 0. All right. Yes. So how could I change this to make it a minus? Okay, if my bounds were -2 to 0, I would be going from numbers that are less than 0, so I would want something that was 0 minus. So if I'm going to infinity, like the ones we did here, we don't need a plus or a minus because there's only one way to get there. If I'm going to positive infinity, I'm coming from numbers that are left of it. We don't need like an infinity minus. We know where we're coming from in that case. Exactly. All right. I would like to integrate this. What's my integral? -1/2. We're going x to the -2. My bounds are a to 2. All right. As I plug these in, I'm going to simplify a little bit. What does a negative exponent mean? Go to the bottom. So I've got -1/2, and this is now going to be 1/2 squared minus -1/2 1/a squared. All right, the first one I can simplify pretty easily. That's going to be -1/2 times 1/4 or -1/8 altogether. Oh, I made a notation mistake. You probably will make this mistake at some point. Find it. Where is my... What? Yeah, my limit went away. That's not okay because my A is still there. Yeah, so I also agree. This process is kind of annoying. I get it. But we got to do it. All right, so here, another scratch work situation. The whole reason I'm doing this process is I don't believe I can plug in 0. And in this case, 0 is actually causing issues. Would you agree? Am I allowed to plug in 0 to that guy right there? No. But I would like to have a pretty specific answer to my question. So let's talk about what happens. What kind of thing am I going to get if I plug in 0 to 1/2a squared? Undefined, be more specific. Be the same thing, be more specific. All right, there's a vertical asymptote. Vertical asymptotes normally go like this, right? Or like this, like this. Where are my hands going towards? Some form of infinity. So I need to figure out which form of infinity that is. This is where the plus or minus can really come in. Now, if I'm thinking about 1/2 times something squared, I think I already know what type of infinity this is trending towards because of the squared. But if this had been an odd power, this plus or minus now becomes important as I figure out which form of infinity I'm trending towards. I'm thinking about 2 over a small positive number, 0 plus is a small positive number squared. That's going towards positive infinity. Now, if I take positive infinity and I subtract an eighth, do I care? No. So this whole thing is just going towards positive infinity. What does that mean about the integral? He diverges. All right, the last thing we're going to touch on really quickly, we actually have done most of the math for it. I just want to kind of explain a little bit. So does anyone notice that this integral looks very much like the one we just did? So we're going from -1 up to 2. So this problem is very similar to this problem, except this time I know exactly where I'm going to break these two integrals. And yeah, we're going to break it at 0, and we are forced into that decision because 0 is the problem number in this case. So when you're working with infinities as your bounds, you can kind of choose anything anywhere between them. Here, we're forced into that choice because the problem number is 0. So we would want to split from -1 to 0 of 1 over x cubed dx. Here, we'd want to go from 0 to 2 of 1 over x cubed dx. All right, we're going to kind of notation out and then just talk out the rest of the question. So here, we'd want to limit out the top bound. Now I left it out, but I'm going to put it in right now. Would this one have a plus or a minus on it? Why? Okay, I'm going from numbers below 0 up until 0. So I want to come from the left-hand side. Think of a number line. I'm going from -1 up to 0. Here, I'd be doing exactly the opposite. I'd be going 0 plus from A to 2. No. Yep. So you can use whatever letters you want. I always just do A for the bottom bound, B for the top bound, just to have like a system for myself. That doesn't matter. All right. Now, one thing you might notice, this is the integral we just did. So this was positive infinity. What I'm going to tell you is if either piece diverges, then the whole integral diverges. Now that's going to be an important discussion once I tell you what the other integral equals. This one, if we went through, would equal negative infinity. Now, some of you might be tempted to say, well, if one of them's negative infinity and one of them's positive infinity, wouldn't it just be 0? No. Infinities can be different sizes. They can do different things. They make things weird. So as a rule of thumb, if one of your integrals in a chain of integrals diverges, then the whole thing diverges. Now, I can't really say what that one would be equal to because I don't know whether that negative infinity or that positive infinity is bigger. So I'm just going to say that that guy diverges. There is no other thing to say like equal to. So whereas I could say this first one that we did that diverged equals infinity as like a concept, this one doesn't equal anything. It just diverges. Yeah. So that's a great question. If I were doing this question, and let's say I chose to do it as like 2 separate problems. I was like, I'm just going to do this one all the way first. One, and you got this one with negative infinity, you could be done with the problem. You could say diverges, done. Yeah. If you go through the whole process like this, I was just shortcutting us. But if you go through the whole process, you can get negative infinity. So the answer here is just diverges. Yep. All right. So So the reason I'm gonna skip the last page is it's just extra, like extra in the sense of like too hard. So just be aware that improper integrals can be a part of another method. So let's just see if you know what method might you use for these two questions. So I'm going to give you 2 very quick minutes to talk it out with your neighbors. I want you to tell me what would you do for the improper integral part. So what would you do from what we learned today? And what method do you think each one of these would use? You have 2 minutes, go. Yeah. If you're not going to take one and start dividing it by like 0.01. Oh, it's getting really quiet. Yeah. Am I okay? Yeah. Just tired. All right. Are we all ready to answer my questions then? All right. So, first one, talking with this improper integral, what would you limit out? Ooh, okay. We're already going here. Does anyone know what I'm trying to ask with? I love that idea. Does anyone know what I'm trying to ask you about the limit? What limit as what approaches what? Would yeah, we would need to limit out this infinity. Is the 0 causing any issues? Is there going to be any other number that would cause issues? Yeah, -1 or -3 would cause issues, but those aren't in my interval. I'm talking 0 to infinity, so I wouldn't have to worry about like breaking this into 2 pieces. What? What would I do if they cause problems? They make the bottom 0. All right. I like the idea of factoring this. Why? What method? Partial fractions. If I were to do a question like this, what I would probably do is partial fractions off to the side, then return with whatever my antiderivative is to then plug in the bounds. All right. What would you guys do? Yeah, I would just take this integral off to the side without bounds, find that antiderivative. When I come back, plug in the bounds, do the limit, all that stuff. So that would be a really excessive problem that is most likely not going to show up on any quiz or test. All right, thoughts on this one? Any thoughts at all? All right, B approaches positive infinity again. I like that. So 1 to B. Thoughts on method? Ooh, IBP. I like that. So that was oob vidu. So any thoughts on U? I would go the X here for my U, but I like the mention of the -X. What's that going to do? You're going to have to do a little bit of U sub, kind of like that 2x we did at the beginning. But we could do our dv is e to the -x dx. So when I integrate the U sub, I'm talking about -e to the -x. All right, but that would be a really good choice. I have put this one on the test before. It was aggressive, and I highlighted it a heck ton, so I probably wouldn't do that to you guys. That was a year that everyone was very into math. Every now and then there's one class that's just like, I remember that year the English teachers were like, you must really like these kids. And I was like, yeah, I'm having a great time. Yeah. Ryan Thomas's year. Yeah. All right. So we are technically done learning this. All of integration techniques, if you will. So as we kind of move towards the end of class, yeah, there's a lot of choices. What I would recommend doing, how I would recommend studying as we approach this test. One, you're gonna want to do problems, and the best way to study is to just do more problems. What you should probably not do is let other people start the problems for you. What I mean by that is some of the hardest decision-making stuff is what method am I going to use? If I'm doing integration by parts, what's U, what's V? Those choices are the hard part. So for this test, I might actually use 3 different colors of highlighting. One that's like big mistakes, one that's like silly mistakes, and one that's like you just need to start over. Because the choices are really, really important. So if you choose the wrong method, you're not going to make the problem work. It's okay to choose wrong. You just have to know when to start over. So if you find that as you're practicing, studying, and practicing with your problem set, you want more practice, I remember when I learned this, I felt like I needed to do way more problems than was just in my regular homework. So I did more problems and I felt better about it. If that's you, more than happy to provide you with more problems. But you're gonna want to practice from a fresh problem. So I'm mostly just encouraging you, please make sure you are doing your own problem set. If you are not doing your own problem set, I'm gonna be able to tell. Yes. What's big as you here? Best choice, things you can't integrate. I can integrate both of those. Next choice is anything like polynomial, so x squared, x cubed. So if I'm choosing x, worst choice, things that cycle, e to the x, sine, cosine. All right. So I would like a little bit of feedback before we leave. All right, I want you. Do I even want to do it?
No, you
Okay. Then everyone get out your problem set. If there is a single person not working on your problem set right now, I will give you that notes check. What? You have a notes check. Perfect. What? Do you want to? Okay. If you want to work on the notes check, you can. I can make it optional, that's fine. I will tell you the second question is a little bit weird, which is why I'm hesitating on it. There's 4. But I think if you want to do one with your neighbor that's the same version, just let me know. So, expectations. You have about 10 minutes left. You should be doing something that is calculus. I'll walk around with these if you want one, feel free. Here are our dates. If we have a snow day tomorrow, expect an email from me with an explanation of what is happening with these dates. But we are done learning. Yeah.
What is flying spaghetti monster? Please bless us with that.
Yeah, there's also what?
First, the flying ticket.
I know.
Always install apps. Okay, so 100% at 6 a.m., 100% at 7 a.m.
Yeah, I would look at this one.
What's it, what's it now? We're gospel. We're gospel.
Okay, I have some music that I haven't read yet. Do you think that'll bring it over? I don't know. All I will tell you is make sure all your corrections are in. If I am around it, like you can hide around it. So if I can have it, I will.
I think I've redone all the well, this.
Yeah, so I will check, I will try to round up. The numbers are set. So if it's within a couple of points, I try to round.
Well, you remember you were
I don't notice that, I feel like it's close to your email, just we can talk, but just make sure all of your correct.
Yeah.
But I think we can. Problem is that you have every other topic the same as every other. You could get creative or you can try to be honest. We have 2 days. Do you guys send me so that I have it in my room? And when you turn it around, ideally, there will be an idea.
I'm like, okay, and you still end up with the same grade.
How is that long? So I don't want to push too far into the.
I like this one.
But I'm gonna try to push it. As long as we're talking before, ideally, what would be nice is if you put it before we do round two, so that you can round two. And then if that's not possible, You're bound to be
Wait, are you gonna grade this next test like this? I can do something.
I'll probably have to people extra days.
Because it's not. I kind of want to. No, wait, which version do you have?
I can give you the same one.
So, you have to try out the virus.
Yeah. So the thing I'm saying is doing more problems, the more problems you do, the easier the choices are. Just like when you first go in factoring and you're doing like a guess and check method, it's hard at the beginning, but it's easier the more problems you run. What times 4x squared? Keep it at square. You're in addition to that. Perfect.
Oh, good. So, is it great this?
What organization?
Here we go.
This is our.
I've done one like 5 times.
Well, everyone.
Yeah, but
Have you done that? You wanna try?
what number is going to
Yeah, that's what. Can you take out
Oh my God.
Yeah, full letters.
Not even gonna worry about it. Right, so I would do your 2 times your $2 plus 6.
I originally
Track down. That's
That's what I was doing. Oh,
you have like a plus 0.
And then oh wait, that's not good.
No, because you want to do what times the 4x squared will give you that. So this is just going to, when you subtract this, that's it.
So I got this far, but like in this problem they have this. Oh wait, for this one.
Okay, so first of all, when I subtract, make sure it's in the negative. And then how much? How do you keep that here? Minus the middle. And that first guy gives you 2. Your infinity should always be replaced, because that's what's making it an improper integral.
Oh, so you did not use
Yeah, that's fine. So then you need to replace your infinity with that b, because that's what you're pushing for. You multiply with the long division is usually helpful when your power is equal or when your power is bigger on the side, because usually if I use of this, when I take the grade, it's going to be 1 power. So like you have to add in.
How do I use them?
Maybe you don't use them.
Oh, you want to
Okay, so then all right, I want everyone to pause. Things that you should know. Oh, I was gonna say some things, and now I forgot all of them. Oh, I know what I'm gonna say. All right, 1. Bring your problem set next time, regardless of what is going to happen, because if there isn't a snow day tomorrow, your problem set's technically due next time. Now, next class, we are going to be doing area between 2 curves, which as far as like pushing second semester BC calculus goes, is like probably the easiest lesson we will do in the second half of the year. So I'm going to try to make that as short as humanly possible to give you as much time as humanly possible to work on your. So do as much as you can, but realize you're probably going to get upwards of a half an hour to work on your problem set, regardless of what happens next class. Feel free to send me emails. I will send you an email if there's any snow or if I decide to change the schedule. Have a lovely day. See ya.